Hello there, my name is Rafael Cunha. I'm a Science and Technology student at the Federal University of Rio Grande do Norte in Brazil, and this video is the presentation of the work IoT Framework with Flexible Management of Multi-Protocol Nodes for Redundancy Applications, done in partnership with the University of Brescia in Italy for the 2021 IEEE Metrology for Industry 4.0 and IoT Virtual Conference. We are going to talk about an introductory part on the concepts of IoT, the device management subsystem and redundancy applications, talk about the proposed multi-protocol architecture, how this feature works and the usage possibilities that implies. We're going to show the results of the experiments using multi-channel as a redundancy solution and show how the user is not affected by the channel itself. And finally discuss our results, bringing a conclusion about the desirable redundancy feature. The Internet of Things has its unquestionable importance since it's transforming the way we live, work, produce, etc. IoT has applications in areas such as security, car traffic, home automation, and healthcare. To support this diversity, the IoT architectures are increasingly modular in order to allow the isolation and technical deepening of each essential functionality. In this sense, one of the essential parts of an IoT architecture is the device management subsystem, which is the main subject of this paper. These figures show the functional view of an IoT reference architecture. We can see that among the many function blocks, the management one is placed vertically, meaning that management issues affect or are affected by many other functions, as well as security. It is interesting to note that usually the communication block is intrinsically dependent on the device itself. This situation in turn may influence the way the service is provided by the device to the framework. In our approach, only the communication and management functions must be modified to support the proposed multipath feature, isolating the responsibility of managing messages to the IoT middleware. Inside the management block, we can see some of its characteristics. The device status represents the state of the device in the application. It's non-existent when a device is not yet inserted into the system or removed. Pendent when the authorization and authentication process, which are also related to the security block, are in progress. Active when authorized, sending live signal and promoting the service availability to the framework, and inactive when the device has been turned off or when it does not give a sign of life in a while. The communication block can support multiple protocols. In this work, we have used Wi-Fi and Bluetooth Low Energy. Among others, redundancy is becoming a key feature for many IoT applications. As a matter of fact, as soon as simple monitoring shifts to control, the need of a reliable availability of data increases. The general way to integrate redundancy into the IoT framework is the duplication of nodes or the use of multi-protocol devices. However, current works found in literature often oversimplify the approach, providing multiple data sources or versatile multi-protocol devices, while leaving unresolved the integration and the management of these assets. The main idea of this paper is to provide redundancy feature without requiring the end user to know details about protocols at low levels. In this work, we propose an implementation of multi-channel, multi-protocol communication between devices and application in order to provide redundancy to the system. So let's describe how IoT devices can rely on a multi-protocol arrangement to guarantee communication success with the IoT middleware. It is worth mentioning that regardless of the protocol used, all communications take place transparently for the user and the communication procedures are carried out automatically by the proposed event triggered framework. This figure shows that after data are generated by the sensor, they are encapsulated into a data object by the application. Moreover, an object ID is added as a new property for the purpose of middleware control. All this process is carried out at the application level, without involving any of the underlying layers. After that, the data object can be queued to be sent through the available communication paths, depending on the preferred strategy configured in the device. The multipath architecture can be used for optimizing different performance indicators. As an example, we can set up the management system to preferably use only one path, leaving the other protocols as a fallback solution. Another possible strategy is to use all the available communication protocols in parallel and send multiple copies of the data object, leaving the framework to deal with the duplicated messages. This case may sensibly improve the robustness of the overall data exchange, but the communication costs, especially from the power consumption point of view, are higher. In this section, we show that data sent by devices and gathered by the framework can use more than one communication protocol encapsulating framework native messages, increasing the chances of a successful communication. The experiment environment consists of a multipath-enabled device. In this case, Wi-Fi and Bluetooth Low Energy solutions have been considered, a BLE infrastructure, gateway plus server, and the IoT framework that is deployed in the cloud as shown in this figure. Two notebooks were used. The first one to emulate a multi-channel device, while the second notebook is used for the BLE gateway and for handling the MQTT protocol. It is important to mention that the BLE path is always configured without confirmation of packet delivery. Consequently, there is no way to retrieve lost or failed to send packets, while the Wi-Fi path can be used with or without confirmation of delivery, as better explained in the following experiment description. A pre-recorded time series of temperature measurements has been used as a synthetic well-known data stream. The original sample rate is 1 sample per second. Each emulation session consists of 1,440 samples sent using the original rate. The main goal of the experiments is to show the feasibility and effectiveness of managing multipath infrastructure for some critical cases in IoT applications. In our first experiment, a device was configured to send the data objects over both paths. In this case, we can validate the reliability of the communication paths by comparing the information reaching the IoT middleware through both paths with the series originally sent. As an additional metric, the delay for transmitting object data over the different paths is also measured. This metric can be used to implement priority strategies. The timestamps needed for measuring the delay are taken in the sending device and in the end-user application, both systems synchronized using NTP protocol. This figure shows the time series received by the IoT middleware through both Wi-Fi and BLE paths. All the data have been successfully delivered with no errors, as a reflection of the favorable environment. On the other hand, the suggested architecture can also be applied to real outdoor environments that may have hostile conditions, usual situation for LP1 protocols. This figure shows the end-to-end delay of each path used for sending data from the device to the IoT middleware. As expected, the BLE path, which uses a gateway as an intermediate data forwarder, takes more time to deliver the data. This table shows the basic statistics for these two paths. We can see that Wi-Fi is faster and more stable, as confirmed by the mean and standard deviation. In the second experiment, the device was configured to work in a so-called priority mode. This strategy is useful when one of the two paths is considered the primary one, and transmission on the second path is a fallback solution occurring only when the primary path fails. In this case, an indication of transmission fail must be passed from lower levels to the application level. The priority can be decided based on reasons like cost or reliability of the channel. In this experiment, we used BLE as a secondary path, retransmitting data whose delivery was non-acknowledged by the primary path. This experiment aims to show that if a device is unable to send data through a path and it knows from indication of the lower layer the non-receipt of that data, it can switch to other paths in order to keep the entire system running smoothly. This figure shows that there was no loss when the communication was temporarily lost by the primary path. The red dots are the BLE data sent when the Wi-Fi channel was unable to deliver the packets. In the third experiment, we configured the device and the framework to operate in real data redundancy mode. It means that all the data are sent twice, that is, through both paths. The IoT middleware in this case must handle incoming data, discarding duplicates, and delivering only a single time series as valid data. In our setup, the Wi-Fi is faster in delivering data, so it usually resembles the preferential path, and the middleware store only data traveling on the Wi-Fi path. To simulate the redundant behavior, we have defined some object data IDs to be selectively discarded in the Wi-Fi path, thus forcing the middleware to output and store data coming from the slower BLE path, since no previous data with those specific IDs were received. This figure shows the part of the received sequence coming from the BLE path, represented by a red X on the image. This means that the proposed middleware is able to seamlessly integrate data coming from both paths, correctly picking the fastest and discarding the following duplicates, if any. This paper describes a desirable redundancy feature applied at the application level on a IoT architecture based on multi-protocol devices. The goal is to ensure the communication between devices and user applications by transparently adding more protocols to the IoT framework. This adds many possibilities for the architecture since it can be used to cut costs by an opportunistic redundancy scheme, as shown by the experiment's results. The demonstration experiment shows that, independently of the protocol, the messages are sent to the framework seamlessly and the users are not affected by how the messages were sent, greatly simplifying the management and of redundancy applications. Since the proposed architecture can be used with more than two protocols and channels, the future investigation activities will be focused on the development of LoRaWAN support for long-range connectivity. And that's it. Thank you.